And I'm telling you one of them is actually very different than the other ones. And here is 17 dimensions about their food. And I think the thing I was trying to tell you is that it's quite difficult to stare at this and figure it out. So I cannot figure, when I stare at this and look at them, they all look basically the same. And this is the thing, the countries, one of them is different than the others, but they're very correlated. So that even though they're 4 countries, and I told you 3 of them are related, and one of them is the odd country out. Even the odd country out is still pretty related to the other 3, so they're very correlated. It's hard to see which one is different. Let's see what you guys said. Did you guys come to a consensus? I don't remember what the right answer is, because they all look so similar to me. Okay, 11 people said second column. I believe that is the right answer. So what is it about, because if you just stare at this for a second, it really looks like there's no difference. Like, the second column looks very similar to the other 2, or the other 3. But I guess there were some hints you guys picked up on. What were the things that made you pick second column? Anyone want to share? Yeah.
Alcoholic drinks. So this country is drinking a lot less alcohol.
Okay. Yes.
And they are
right.
eating potatoes very larger in quantity compared to others.
Okay. So yeah, alcoholic drinks they had a fair bit less. Potatoes they had a fair bit more.
And fruits are also less compared to others.
And fruit is a little bit less. Okay. Yeah. Right, okay, so this is good. So if you stare at it for long enough, you can eventually see the differences. I guess you have to be careful, right? Because alcoholic drinks, they had less, but but there's probably other countries that have less in different categories as well. So it's like how much less is less. But I guess they are less in a couple other ones. Like fish, they're also a little bit less. So it's true, if you kind of stare for long enough, you figure it out. And you guys did. I think you all got it right. Okay. So great work. Picked up on these subtle hints. Now imagine you're trying to tell a computer how to do it, right? Find the odd one out. It's a pretty tricky task. It's what, in some categories it's less, in some categories it's more. What do you kind of say would be tricky to do? But a simple way, what we talked about last time we did all the theory behind this PCA idea. And PCA is the idea of reworking your dimensions. Change the basis you're looking at. So instead of looking at alcoholic drinks as one dimension, beverages as one dimension, meat as another dimension, cereal as another dimension, we're going to make this a new dimension, which is going to be a linear combination of all these things. And the linear combination we chose is specifically chosen, you saw the derivation last time, to spread them out as much as possible. So these 4 countries will be spread out. We'll have 4 dots in 17-dimensional space, and we've chosen the specific direction that makes them as different as possible. And then that way, maybe we can see what's going on. And there's a really nice website that this is taken from. I believe this website. Yeah, here it is. So here's the website. Okay. And here is the thing. So here are the 4 countries. And the 4 countries are England, Northern Ireland, Scotland, and Wales. And if you know geography, these are the 4 countries that make up the United Kingdom. So the United Kingdom has 4 countries in it, the same way Canada has 10 provinces and some territories. They have these countries, and these 4 countries together make up the United Kingdom. And one of them is very different than the other 3. And you guys identified it is the second column. It is Northern Ireland. That is the really different one. Why is Northern Ireland different? If you know geography, again, this is obvious. But let me show you a map of these countries that I got ready. So here are the 4 countries. Scotland is up here, England is this big green one, Wales is over here on the left, and where is Northern Ireland? It's not even on the same island, it's on a different island. It's over here, on the island of Ireland. So Northern Ireland is part of the United Kingdom, where Ireland, regular Ireland is the rest of that island, and they're separated by an ocean, well, a piece of an ocean. So it's very different. It's of the parts of the United Kingdom, it's off on its own. When Brexit happened, there was all this stuff of how are we going to do borders, because we'll have to have a border here, because Ireland is now in the EU, and Northern Ireland is not in the EU, so how is this going to work? Quite tricky stuff. So Northern Ireland is very different. We know that just from the map, and you guys were able to see that in the data. You were able to see it in the data, but it's quite tricky to see, because it's mostly the same in a lot of ways. But now let's see what happens if you do principal component analysis. So principal component analysis, you have these 17 dimensions. You'll get 17 dimensions of new dimensions, the principal component 17 dimensions. And like we said, the first one, they're ordered. The first one is the largest eigenvalue. That one is the most important. So let's just plot these 17-dimensional things, turn them into one number, which is the first principal component, and see what it looks like. So let's see what it looks like. And here it is, PC1, the first principal component. All of the countries are just one number in the first principal component. And look, Wales, England, and Scotland are over here, and Northern Ireland is all the way over here. So now imagine I gave you, instead of the warm-up problem this morning being, here are these columns, find the odd one out. I said, here are these 4 dots, find the odd one out. You say, okay, it's that one. They're very, very easy. So the principal component lets you immediately see the pattern that's hidden inside, is that 3 of them are a lot more similar than the other. 3 of them have this first principal component direction is very similar, and the 4th one is very different. And of course, you have 17 principal components to work with. Already just one is telling you a lot of information. You could do 2 of them. You could do 2 of them. So here it is with 2 principal components. So the first principal component is on the x, and the second one is on the y. And you can very clearly see the separation, and you can see that somehow Scotland is a little bit more different than Wales for some reason. So it's a great way when you have data like this, that's like really high dimensional, to sort of get at the essence of what's going on. Okay, and of course, these principal components, before, they made sense, like they were like the amount of fish, the amount of fresh fruit, and now they're just these like abstract things, because PC1 is a linear combination of all the different things. So it's some amount of fresh fruit plus some amount of potatoes plus some amount of alcohol. Some of the coefficients might be negative, so it's like you take the amount of potatoes minus the amount of 0.3 times the amount of alcohol. Like it doesn't mean anything anymore, but it somehow captures the differences in the data. So especially when things are really highly correlated, it's a really good way to visualize the data. Any questions or comments about that first example? Okay, so in today's class, we're going to do lots of examples like this one. And you've seen sort of one example already. I found a few of these websites that I really like that show lots of nice visualizations. And this one, it has these nice sliders, which are kind of equivalent to what we did last time. So last time we had, in Desmos, we had these 5 points, and I said, what is the direction? What are the principal directions? And it turned out there was that red direction and that green direction. And if you map them, then these 5 purple points get mapped like this, and you can see they're maximally spread out along the PC1 direction, and PC2 is whatever is left over. And the cool thing about this website is you can move them around and see how things change. So what if one of them was over here? Now the data set changes like that. So this point is pulling the principal component with it. And so you can play with that and see how it works, kind of very similar to what we looked at last time. Okay, so mapping from the original to the other thing. Okay, here is a 3D example. This is beyond what I can normally do. And so in this 3D example, here are the pictures in 3 dimensions. And you can see that there's 3 blobs. You can like visually, like your human brain is good at 3-dimensional stuff, you can see that there are 3 blobs. But if you looked at the x, y, and z components directly, right? And this is what the computer can see, is the x, y, and the z components, which are the original variables. It's hard to see that there's 3 blobs, right? So it would be kind of tricky to explain to the computer, look, there's actually 3 blobs here, based on the x, y, and the z. But once again, if you do principal components, it looks like this. And then you can start to see it doing things. So here is principal components. I've taken the data set, I've applied the principal component analysis, and in the new dimensions, again, there's 3 principal components, because there's 3 dimensions. Principal components is just a change of basis. There's PC1, PC2, and PC3. But they're somehow aligned with the actual data. And if you throw away PC3, which is the least important one, you have PC1 and PC2, and you can sort of see the 3 blobs in PC1. So if you look just at PC1, you can see there's 3 blobs in PC1. So somehow, if your job is how many blobs are there, looking at the PCs is a lot easier than looking at the X, Y, and Z, because the blobs are very mixed up in X, Y, and Z, but are more separated in PC1. So that's another example. Same idea as with the countries. You can sort of tell things apart more easily in principal components. Any questions or comments about that? Okay, so today, like I said, we're going to do a lot of examples of things you can do with principal component analysis. And I want you to use your imagination and think of what kinds of things can you actually do? Which of these can you do? Which of these tasks can dimension reduction, so going from many dimensions and then throwing out some of them, can help you? Select all that you think might work. So you can select more than one, And we'll go from there. So take a few minutes and think, what could you do with this stuff? Now you've seen one example. We'll look at some more. Maybe a minute and a half. Okay, a few seconds left. Okay, let's see. Which of these tasks can you do? First column, second column, third column, fourth column. There's some kind of bug because those are not the answers here. Let's try. Let's see what it says this time. Okay, so 13 people said visualization, 12 people said clustering. Visualization and clustering are kind of what we just did, right? So here we had some data. Not on this site, but on this site, right? This is a great example. This is hard to visualize. It's already in 3 dimensions. Imagine it was in 17 dimensions, like the other one. Hard to visualize. And then you do a PC, and then you can kind of immediately see the main structure. So same idea over here, something tricky to visualize. Same idea was with the actual countries, right? Very hard to visualize this, but this is a lot better, right? So you can kind of help you visualize some data by doing this stuff so your human brain can understand it. And it lets you do clustering, right? You can see there's 3 blobs. All of these things should kind of go together. Those things should go together, and those things should go together. That's what clustering is. And we did the same thing over here with the countries, right? So these 3 countries should go together. That country is in a different cluster, right? And it matches geography in this case. So those are 2 things you can definitely do. 2 things you can definitely do. Classification tasks, 14 out of 14 people said, we will get to that one. That's definitely something you can do. Only 9 people said regression. And while both regression and classification just mean you have, in addition to the x's, you have some y's, and you're trying to match the x's and the y's by either doing mean squared error or cross entropy loss or something. PCA is something you do only on x's. So very strictly speaking, classification and regression is not like the same thing as PCA. PCA you only do on the x's. You have some x data and you do something with it. But the question says, which of these tasks can dimension reduction help with, right? And so the idea is, for classification and regression both, first do PCA, then do all the stuff we did earlier in the course. And in both cases, it will help. And the reason is, again, because, like you saw, say for the housing data set, some of the columns are kind of noisy and don't matter, and like ideally, you just drop them. Like when you do feature selection, for example, you just delete some of the columns. And PCA says, we're going to combine everything into the most valuable directions. We're going to squeeze the juice out of all the columns we can by combining them in the best way. And so it's sort of pre-doing this kind of thing for you, right? It's saying, this is the most important thing I can come up with is this particular thing. Let's use that. So, and it's the same thing for both classification and regression. So I think it's interesting that 14 to 9, people like classification better than regression. But it really is, in my brain, it's the same kind of thing. It's like you take PCA, you're kind of taking the essence of the inputs and you're working in these PCA directions where things are as good as possible, as representative of the data as possible, spreading things out as much as possible. And then you can apply all the stuff we did with the y values to that. So I'll show you examples of both of these. Any questions or comments? It's interesting that so many people like classification but not regression. Maybe you guys thought it was a trick question and one of them had to be not selected. Questions or comments about that? Okay, so let's see a regression example first, because I believe that was in the video from last time. So this is PCA. This is I have a mathy one and then I have a housing data set one. So here is a mathy one, which is the correlated data we've seen a bunch of times before. So there's x1 to x5, there's y1 and y2, and the x's are highly correlated, and the y's, one of them depends only on x1, and the other one depends on all the other ones altogether. And if you do regular regression, you get stuff like this, when you get like a RMSE of 0.95 for one variable. So if you're doing y1 and x1 and so on, and this is where this example data set, we've done a lot of things on it. We've done feature selection, stuff like that, and now we're going to do PCA. So what I do is I take the x's and I apply PCA. So this is the forward variable selection we did before, where we automatically found the best number of variables was 1 for y1, and for y2 it was 4. But now we're going to do it with PCA. So first what we do is we apply PCA to our data set, and that gives us some new values, these PCA things. And one of the things it tells us is the explained variance ratio. And it gives us this list of numbers, 0.83, 0.1, 0.03, 0.01, 0.01. And these numbers should add up to 100%. They should add up to 1.0. And they tell you how important each of the PCA directions are. So this is what the video today was about, was this idea of not only do the PCA directions tell you something, which were the eigenvectors, those are the most important directions, but the eigenvalues sort of tell you how important each direction is. And we've specifically done it so the first one is always the biggest eigenvalue, the next one is the next eigenvalue, and the next one is the next eigenvalue, and so on. That was how we did it mathematically. But how big are they actually in practice? You can ask the computer, please tell me. And this is what it's done. So this is saying that 83% of the variance of all our points is captured just in that first direction. 83% of the spread just comes from the PC1 direction. And the PC2 direction has 10% of the spread. So that means if you include PC1 and PC2 together, you've captured 93% of all the variation of the data. And this is great news. So if you see something like this means your PC, your principal components, will work quite well. And it's coming from the fact that the data was highly correlated, right? So sort of like x1 and x2 on their own don't tell you stuff because they're in such the same direction that you can make this principal component and it will capture 83% of the data. And so here is the new basis that you work in, and you use this command pca.transform. You take the data, you transform it, you work in a new basis, and here is the new basis of the PCs. The x's were this highly correlated mess, right? So if you draw the correlation function for the x's, they were highly correlated. Like x1 and x2 are very related. What does PC1 to PC2 look like? Did I plot it? I hope I did. I didn't. Okay, let's try to do it. Let me see if it'll work. Probably it'll have a bug and not work. But let's run everything, and then I wanna see what the correlation is, because it should be more or less perpendicular. Let's draw this picture. Okay, here is the picture. Let's do this for the PCs. Did it get that far? Forward variable selection. Here it died. Why did it die? Argument. Okay, yes. Yes, it doesn't like argument. Okay, let's run everything else. Variance of the components. Then I transformed it, but now let's add in this to plot the PCs. So I called the directions PCA1, PCA2, PCA3, PCA4, and PCA5, and let's look at their correlations. And it's not the DF anymore, it's the PCA DF, the PCA data frame. Okay, so hopefully this will work. Okay, so here's what it looks like, right? Before it was highly correlated. X1 and X2 were almost the same thing. Now look at it, we've transformed the data. PCA1 is very correlated with itself. What is the correlation between PCA1 and PCA2? 0.00000001. So we've sort of taken all the correlations in the data and we've moved them away by just doing a change of basis. So before you can think of they were in this long ellipse, and now we're working in the directions that are aligned with the ellipse, so that the data is the actual coordinates we're using are actually independent. They're uncorrelated in this sense. So very nice property to have. Okay, and if you do the regressions, you should get some better results. So y1 and y2, and here's the subset selection. Okay, so is it going to yell at me because this argmin versus IDF-min thing? Okay, well, okay, we can see the data. We just can't. The computer did all the work. It just can't tell us which one is the smallest one because there's some sort of technical bug. So we'll do it ourselves. So here we try. We're doing subset selection using the features PCA1, PCA2, PCA3, PCA4, PCA5. Of course, we know 1 and 2 is supposed to be better than 3, and so on. So it should really come out to 1, 2, 3. But we let the computer do it. And you can see PCA1 is the best one out of all of them if you're just going to use one feature. And that gives you an RMSE of 1.38. If you're going to use two features, then PCA1 and 2 is the best. And then you get an RMSE of 1.15. And if you use PCA 1, 2, and 3, it's RMSE of 1.09. And so you're kind of getting most of the gains by just the first two coordinates. So if you start a very simple regression with only two coefficients, then PCA 1 and PCA 2 is a great thing already. PCA 1 and 2 and 3 is a slightly better, but if you use PCA 1, 2, 3, 4, it's slightly worse. Oh, PCA 5 is somehow better. Okay. Some sort of weird coincidence. Okay. So that was for y1. You can do the same thing for y2. And I guess it'll look something like that. And so what is the moral of the story? Is that you can replace this idea of doing... Oh, here's a nice plot of what it looks like. You can do all the things we did before. You can do them with the PC directions. And they're uncorrelated. It solves this multi-collinearity problem that some of you guys were worried about before. And things work quite nicely. You can even skip doing this stuff and just say, I'm just going to do them in order. Now doing them in order makes sense because they are in a special order. Okay, so that's like a very simple regression problem mathematically. I'm going to do another one with the housing data set in a second. But any questions or comments about that? Okay, let's do the same kind of idea, but for this housing data set. And this is a slightly different housing data set than you guys had. This is in R, by the way. This is an old code I had from many years ago. And it's a different housing data set, which is some Kansas housing data set. And the nice thing about this housing data set that I like is it has these columns. It has things like square foot lot. That's something you guys had as well. How many square feet is the lot that the house is on? But it has these columns, square foot lot 15. And when it ends in a 15, that means it is the average of that value, not for the house you're selling, but for the 15 closest houses to it. So square foot lot is how big your house is. Square foot lot 15 is how big your neighbor's houses are on average. And of course, these things are going to be highly correlated. So square foot lot and square foot lot 15 are very highly correlated. Same thing with square foot living 15. Those are highly correlated. And if you plot what it looks like, here is a plot of square foot living 15, how much, that's your neighbor's, square foot living is your house. So how big is your house versus how big is your neighbor's house? And you can see it's very highly correlated. And you can look at the log price. So this is how many zeros in your price. These houses are worth tens of thousands of dollars, 5, and these houses are hundreds of thousands of dollars, 6. All the way over here is like 6.5, so halfway to $1 million on the log scale. And so these are very highly correlated. It's very easy as a human to say, of course, there's this diagonal direction. That is the direction of increasing money. And this is the perfect thing to do principal components. When you do principal components, it will automatically find this direction and say, okay, the main variance is in that direction. That is the direction we got to look at, and that will classify the houses better for you. So if you apply principal components first, first I did regular regression, regular linear regression, and how much error did we get? So these are the coefficients, and we got, what did we get? Let's look at the standard error. It was 0.15. That was using all of these different things. So 1, 2, 3, 4, 5, 6 variables. We got a standard error of 0.15. And now we're going to do some PCA. So like before, when you do PCA, it comes with this proportion of variance explained. And you can see that 53% of the variance is sort of captured by PC1, 25% is captured by PC2, and 10% is captured by PC3. So between PC1, PC2, and PC3, you've got most of the stuff going on. PC4, 5, and 6 don't explain a lot. There's not a lot going on in those ones. And you can kind of see that already. It also gives you the cumulative proportion if you want to add them up. So by the time you get to PC3, you're at 90%. PC4 is 96%. And again, this is happening because there's a lot of correlation, right? So square foot and square foot 15, almost the same. And the PCs kind of automatically take that and use that. Okay, and then now you can do, you can also plot it. So here's a plot of what it looks like in PC land, PC1 versus PC2. In this plot, somebody has overplotted what the original things are. So on the plot, PC1 versus PC2, square foot lot is in this direction. And I think these ones are the size of your house is that direction, and this is the size of your lot. Which again, I think they talked about this in the videos as well. So if you saw the videos, you'll know what these mean. Okay. And here it is, again, with the prices overlaid. And you can see that PC1 on its own is already doing a pretty good job of predicting the prices. So PC1 is on the bottom here. And you can see that as you vary PC1, you vary the prices. All the expensive houses are over here. And as you go this way, cheap houses. PC2 also is telling you less about them, right? They're sort of almost the same color in each column. And that tells you that just regressing with just PC1 will have a good thing. So if you do regression only with PC1, with one single variable, you get a standard error of 0.17. So before we did a regression with all of the data, and we got 0.15, and we did it now with just one variable. So this is y equals mx plus b, literally. No beta 1, beta 2, literally just one variable gets us almost the same goodness of score. And if you imagine you want to make it a little better, you do PC1 and PC2, and now you really are 0.162. You're getting very close. PC1, PC2, and PC3, that will give you 0.158, which is very, very close to the original thing. So you kind of reduce the variables you have to use instead of having a big mess of all these different variables. First you do PCA, you reduce the dimension, and now you have plots you can look at more easily, and you can do regression, and it'll work almost as well just using the first few principal components. Okay, here's with 4, and we got, I think, the same score as with all of them. That's because PC5 and PC6 just don't contain any useful information. Okay, any questions or comments about this example? So this is one thing you can do with PCA is use it as a layer in your data preprocessing, if you want. Okay, let's go back and see what were the other fun things you could do. So far we've done clustering and visualization. We did those. We've done some regression tasks. Here's another one that I want to talk about. Actually, let's go to the list. I have a little list. Here are a little list of different things. Okay, so this one has something about image compression. And this is another thing you can do with PCA, right? And we've already talked about this idea. You have 17 dimensions. You compress it down. You switch to the PCA land, and then you just delete everything except PC1 and PC2. So this is saving you some time. You can do what is called compression. And in this picture, they have some nice math. This is a repeat of the math we did last time in a little more detail with eigenvalues and eigenvectors. But they have this really nice example with a picture over here that I really like. Let me find the picture. So here's a picture, and imagine you need to store this picture on your computer. Okay? So you have this picture, and you want to store it on your computer. That would be a lot of things to write down. You need a number. How much is this pixel? How much is that pixel? And so on. A lot of numbers to write down. And that's because you're working in pixel space. And in pixel space, this is like a 1,000 by 1,000 image. You've got 1 million pixels to write down, let's say. However, if you treat this as a matrix, and you do this thing, let's see what we can do. Let's see if we can reduce what we need to write down. So instead of thinking of each individual pixel as a component, and this is something with 1 million components, what would happen if we worked in the eigenbasis? We did principal components on this picture. And here is a plot of the size of the eigenvalues sorted. And this is a lot like what we were doing. We said the first principal component contains 80%, the next one contains 20%. That's the same thing as saying the first eigenvalue is much bigger than the second eigenvalue, and so on and so on. And you can see that in the first 5 or 10 eigenvalues, that contains most of the thing, right? If the eigenvalues were completely flat, then we wouldn't be able to just lop off a bunch of them. But if we throw away all the eigenvalues past 30, then we're not going to lose a lot of data. And you'll see that visually in this picture. So here's the original picture. This is the size of the eigenvalues. And here are what the eigenvectors look like. So this is the first principal component. If the thing was an image, then the first principal component is a vector that is some other image, right? But this is an image that is low rank, right? So you can see it in every column and row. It's the same thing. Here we have the sum of the first 5. So just using the first 5 principal components, we have that picture coming up. And here we have, can I move over a bit? Here, I have to zoom out. Here's 9, 13, 17, 21, 25, and 29. So to draw this picture, you need to know 29 numbers. It's a lot less than 1 million numbers. So we've gone from the original image to this image, and we've compressed it down to just knowing 29 numbers. And this is because in real life, there's a lot of things that are simpler than the space of possible images. The space of possible pictures includes all sorts of static pictures that like are black and white and change all the time. But real life pictures don't do that. And so real life pictures are highly compressible. And this is one way you can compress them down from 1 million numbers down to just 29. Okay, I think this is really cool. When you actually take a JPEG or something, it does this using the Fourier basis. It really does this kind of thing. And that is why you can transmit pictures and they're only like a megabyte big instead of being like hundreds. Like if you had to write down every single pixel, it would be hundreds of gigabytes. Same thing with MP3s. This is how they work. Instead of a waveform where we keep track of what is the microphone doing hundreds of times a second, we just write down in the basis of the Fourier basis, and we write down the coefficients in front of the first 29 principal components, and we throw away everything else. So this is a method of compression, of storing stuff better. Any questions or comments about how that works? We're going to see more examples like this with faces and other things. So this is on one single image or one single recording, anything you want. As long as it's a vector, you can maybe rewrite that vector in a useful way by doing the principal components and only writing down the first few principal components, throwing out the rest of the principal components. Okay, let's look at other examples that we have. Okay, another thing you can do is for classification. So we did regression, and here is an example with classification. In fact, I think I have this one open as a PDF. Let me see if I can open the PDF. I want this book, because I remember there was a bug when I was looking at this the other day. PCA and high dimensions. So this book is called The Mathematics for Machine Learning. This is the book we use in one of the courses for the CARE AI program, the Cooperative Specialization in AI. And they have a whole section on PCA. And they have one example that I really like, which is using the favorite data set that I told you about before. So first of all, they have this nice hands-on thing on how to do PCA, but they use it on this nice data set of digits. And so do you remember the MNIST data set we did a few classes ago, where the data set is digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I think there's a picture of them. Where is the picture of them? Well, okay. Here are all the digits 8. And here is them doing the same thing that I did with that picture of Audrey Hepburn before, but now doing it on the digits. And so you take these 8s, and you can apply this PC idea to all of them at the same time. So here are 4 different 8s, and here are the principal components. Using only one principal component, you can represent these different 8s. And you can see that it kind of takes into account, even just with one principal component, you can tell the difference between this 8 and that 8. One of them is going that way, one of them is going this way. And as you add on more principal components, you can get very close to the original. Right? So by doing this, you can take your space, which originally was 784 pixels, right? Originally, you had 784 dimensions. You can reduce it down to like 10 dimensions with just a little bit of loss. It's still pretty good. And now you're just working in 10 dimensions. It's a lot easier to work with. And you can do this not just for one digit at a time, but you can do it for all the digits. So let's see what it looks like. Yeah, so you can plot all of the 8s, and then you can start to say things like, oh, these 8s down here are one kind of 8. Those 8s over there are a different kind of 8. But you can do it for different digits. And I believe they have one with 1s versus 0s. 1s versus 0s. Where are the 1s versus the 0s? I must have passed it. Eight, 8, 8. Here it is. Here's the 1s versus the 0s. Okay, and this is the bug that I found the other day, so I'll reopen it. But it says the 1s are orange dots and the 0s are blue dots. So here we have mapped the 1s and the 0s into a two-dimensional space. So every 784-dimensional object is mapped down to 2 dimensions, and you can visualize the difference. The 1s are supposed to be colored in orange, and the 0s are supposed to be colored in blue, but it's not working. So let me get the same exact page open from the book as a PDF, and then it will work. Here it is. And I want to go to page 338. Oh yeah, okay, here's the digits, 0, 1 to 9 that we saw before. Here's the kind of picture we had before, direction of maximum variance, all this stuff. So it's a really nice place where this stuff is all nicely written. And if you go to page 338, you will see the 1s versus the 0s in color. Here it is. And now it's working. Okay, so we've taken all of the digits and we've mapped them down to two-dimensional space. And you can see they naturally organize themselves into classes. So you can imagine if you're trying to figure out a 1 versus a 0 in pixel space, in the original 784-dimensional space, is quite tricky. But if you're trying to figure out 1s versus 0s in the two-dimensional mapping of the first two principal components, it's quite easy. Everything over here is a 1, everything over there is a 0. So by mapping it down, you can better classify things. So a nice example of that. Do I have a notebook there as well? Any questions or comments about this idea? This one you'll see, and this is what we're going to start next week and next class. We're going to start doing machine learning type things, and you're going to see that this is a linear way to embed the digits into two-dimensional space. You can also do a non-linear way, and you can get even better results. So we'll be doing that next week. So this kind of picture will come up again in the course. I think this is such a cool thing that you can take images and treat them as points in a two-dimensional space and then say something meaningful about them. Okay. Let's see, do I have housing data? This one, okay. Okay, and this was this. This was that, okay. All right, so we're gonna do a few more examples of different things. Yeah, okay, I think this one has going down. So this idea of, yeah, question.
Yeah, so the zeros and one that you have plotted in the previous graph,
Yes.
are they in the PCA1 and PCA2 direction?
That's right. So originally, each image is a 784, a vector in R to the 784 because it has 784 pixels. So I took these 784 dimensional things, it's a big data set of tens of thousands of these images. Then I did the PCA on the big data set, okay? And then once you do PC on the big data set, you have a new representation with PC1, PC2, all the way up to PC 784. And I deleted everything except for PC1 and PC2. So that 784 dimensional vector becomes a two-dimensional vector of just what is PC1, PC2 for that image. What is PC1, PC2 for this image, and so on. And if you plot all these images, they naturally arrange themselves by what the value of the digit is. So originally they're all mixed up, right? Like in 784 dimensions, this one and this one are actually quite similar because they just have about a bunch of white pixels somewhere in the middle. But now in the two-dimensional space, the PC space, they're quite separate. And that's because the principal components somehow capture what's actually going on in the data. It captures the difference between a 1 and a 0. Yeah. Yeah, great question.
But the image, I mean, you're getting this data by plotting it out on 2 dimensions.
That's right, yeah.
But the image would be still blurred, right?
Well, so the image is 784 dimensions.
Yeah, but if you plot like image for PC2, like PCA2,
yeah,
that'll be still blurred, right?
Right. So I think you're asking about the reverse direction. So what I just explained is how you go from 784 dimensions down to 2.
Yeah.
I think you're asking about how would you go back? Like if you're at this point in space, how do you turn it into an image? And you can just add up the two components. You'll get something that looks like that other thing we saw for 8s. Let me see if I can find that thing for 8s. Where was the thing with the 8s? Yeah, maybe down a bit here. Maximum variance. Ones and zeros. And then we have these 8s, right? So the 8s are showing you how you can reconstruct.
Yeah.
So this is a 784 dimensional image in the top row. And then below it is what you get if you reconstruct using only the first principal component, one PC1. You get something like that. I think this, in this one, strictly speaking, I think they're doing principal components on each image individually. In the previous example, we took the entire data set and did PC. So it'll be slightly different. But the same kind of thing. You'll get a blurry, if you just use the first two principal components, you can't recover the picture directly, but you can recover most of the information, sort of, in the sense that, you know, of all two-dimensional things, that's like kind of the best. Right? And if you went up all the way up to 100 dimensions, then you can recover it even better. So I think that might help you understand. Okay. Yeah. Great question. Anyone else? Okay. So in this one, they had some examples, and they said, what are the limitations of principal components? And they said if it's non-linear, your principal components won't work. And that's because at the end of the day, the principal components are a linear map. So you're just taking the things, we're doing linear operations to the original things. So you had the original components, x1, x2, x3. We're doing linear combinations of x1, x2, x3 to get PC1, PC2, PC3. And they're showing you some examples where this won't work. So they're saying, what if it's like this circle thing? When you do principal components, the principal component it finds is a line, that red line, going up and down. And then when you map, it's kind of looking quite bad. Like the projections are not working out. And same thing with PC2. So things won't work if they're circles. The nice thing about principal components, if you understand what's going on, it's actually quite simple in terms of eigenvectors and eigenvalues, and there's lots of ways you can modify it. So there's a really cool thing I wanted to show you called nonlinear principal components, or kernel principal components. And this has a nice Wikipedia page where what they do is they say all you have to do is you take this covariance matrix, X transpose, that's the covariance matrix we started with last time. You replace it with something very similar, which is you just feed it through some function, k. So you do phi of x transpose phi of y, that's some new function k of xy. And if you just do the same exact thing we did before, on this new matrix, you can get all sorts of cool stuff. And so they have a nice picture here, which is what I want to show you. So here are some points that are just like that example. There's red points, blue points, and green points, and they are encircled by each other. So if you just do straight PCA on this one, it won't know what to do because the principal components are just vertical and horizontal, and it doesn't know how to separate the greens and the blues. But if you do this kernel one first, then it will work. So close this. Here it is after transforming. So if you do kernel PCA and you use the right kernel, then it can separate out the points. And so somehow you can incorporate nonlinearity by just doing a small change in what's going on. So PCA, I think, is not the end-all and be-all of all possible things you could do. It's kind of the most basic starting point, and you can change it in all sorts of ways. And here, so they've applied some nonlinear function through the PCA, and now it is split up perfectly, where the PC1, the first component on the bottom, perfectly tells you if you're green, blue, or red, just by looking at one single dimension. So, and it automatically finds that in the data, which is a really cool thing. So, and here it is, here's another map, same kind of thing, and it's overlaid what it did to the original space. So imagine a grid on the original space is now getting transformed to this nonlinear grid. It's applying this nonlinear map to it, and it automatically finds out the right way to do it to apply the function. So that's a cool thing you can do with it. You can do nonlinear PCA, which I think is really cool. These kernel things are related to some of my research, which is why I'm into them. Okay, let's go back to the list over here. Okay, last but not least, another thing that you can do, again, with images. Yeah, question?
Yeah,
So with kernel principal component analysis,
Yes, lots of them.
are we increasing the dimension first? So like let's say for example, if we are viewing it from the top, like
Yeah.
we can't differentiate. But if we like
Yes.
increase the dimension, let's say z-axis, that will give us the depth. So maybe the
Right.
green point would be at the bottom.
Yeah, this is a great question. So you could think of increasing the dimension, and that would of course make some problems worse. So kernel PCA, it turns out, is equivalent to somehow increasing the dimension and then just using the inner product on this increased space. So I'll go to the math here and I'll quickly show you what's going on. So it's really all about this line over here. So we have this function phi of x transpose phi of y. In this example, phi is a function that maps x to some higher dimension, just like you want it to do. So we take the points and it would map them to some higher dimension. So you could do everything with this function phi, figure out what the function phi is, and then go from there, map everything to a high dimensional space, deal with the problems in a high dimensional space, and then work your way back. But the beautiful thing about kernel PCA is even though it's equivalent to doing a phi of x and a phi of y, you never have to touch phi. You don't even need to know what the matrix, you don't even need to know what the function phi is. The only thing you need to know is this function k, the kernel. And k of xy is the inner product of phi of x and phi of y. And so you kind of are doing something as if you're going to high dimensions, but never ever leaving this space where you just replace the inner product. Before it was the inner product of x and y. Now it's the kernel, k of xy. This is called the kernel trick. Every time you see an inner product, you replace it with a kernel, and it's equivalent to working in a higher dimension, but you skip all the annoying things about working in a high dimension, and you still, everything works exactly the same, except you just, in your code, you replace inner product of xy with k of xy. And by choosing the right k, you can simulate sort of doing high dimensional stuff. So when you actually do it, in this example, they chose this as the kernel. K of xy is x transpose y plus 1 squared. And if you wanted to get x transpose y plus 1 squared, you would have to use a very high dimensional phi to simulate this. But we can skip all that. We just say this is the function, we apply it, and it's kind of just saying use this different inner product, this kernel inner product, and you can get the thing. There's something called support vector machines that have the same thing with the same kernel. I might talk about that in the next few weeks. Yeah, great question. Any other questions or comments? Okay, so as the last example, again, going with faces, there is something called eigenfaces that I really like. And it comes from this math stack exchange post. Real life examples for eigenvalues and eigenvectors. And this is just like when your little brother says, what's the point of learning addition in math class? This person is asking, what's the point of learning eigenvectors and eigenvalues? And so this is a little bit like what we've already seen, but there's this really beautiful plot over here for eigenfaces that I like. And here it is. And here are a bunch of different images of different famous people. And we've taken these images, which are some number of pixels by some number of pixels, and we've taken that as a data set and mapped it down to 2 dimensions. And in 2 dimensions, the people organize themselves into these different directions. And the way we do it is we have the first eigenface and the second eigenface, and every face can be written as a linear combination of eigenfaces, and you can use that for all sorts of things. So I had a student who did a project on this a few years ago, and here are the eigenfaces. So it starts out with the kind of thing we saw before, right? But then he really does this data set, just like from that Stack Exchange post. So here are some pictures. Here's George Bush, which is how many pixels by how many pixels is it? Well, I guess you'd have to count them. Okay, there you go. So I think each one is 1,850 pixels wide. But here are the eigenfaces. Here are the eigenfaces, and here is a list of the variance explained by the first 10 eigenfaces. So here's the first eigenface. That explains 20% of the variance. So just knowing how much they look in this direction is 20%. This one's 14%, 7%, and so on. So it's not as good as the housing data set where it's like 80%. But if you add up the first 10 eigenfaces, you can do a pretty good approximation of anybody's face. So very similar to what we saw with that Audrey Hepburn picture before, but now on several different things. Here are the least useful. These are principal components 91 to 100. These ones are just like pure noise. So these are the most useful ones. versus the least useful ones. And you can reconstruct people. So here's the original picture. And here you can reconstruct them using the first 100 eigenfaces. So there's the original. Here's the first 100. Pretty good. So we've taken the data set and we've effectively reduced the dimension by like a factor of 10. A much lower dimensional space. Okay. There you go. So 100% each. And here they're talking about like how long, you have 11% of the memory of these things. And here is side by side the original picture and the projection into this low dimensional space. There's one other one where somebody did this and they used it for facial detection. So it's like, here's how you do facial detection. And they did exactly this eigenface trick, this eigenface, which apparently comes from some old paper. And what they do is to say whether or not you're a real person. So here's the data set they had. And what they do is they detect images by this. So here's the thing. So here is the query, and here's the best match. How did we get from query to best match? Is we looked in the low dimensional space, and we found in the low dimensional space what is the closest point. So if you do closest point in pixel space, it's not very good. But if you do, first you map down to the PCA space, and then you find the closest point in PCA space, then you get a pretty good match. And it should match who it is. And so you can use this to detect people's faces. So maybe you have a camera in front of your door, and you only want to let people in who are allowed in. This is one way to do it, right? You take a picture, you map it to PCA space. In PCA space, you find the nearest match, and then you go back over here. So this is a whole field of vector embeddings, and there's this thing called vector search engines that basically run on this. They do more complicated things than PCA, but it's the same idea. Take the original things you want, map them into some latent vector space where things are meaningful, and then go back out. This is the same kind of thing that ChatGPT does as well. You have text, right? You type in some text, you want to figure out what to write next, you map it to some vector space, find out what to do in the vector space, then map back. So there'll be some more examples of this in the next few weeks, where we're going to do nonlinear versions of this. This is all with PCA, it's all linear, and you can make a nonlinear machine learning based version that kind of runs the same way. Okay, any questions or comments about that? Okay, so now you've seen a whole bunch of very different examples of these PCA things. There's a few more here if you want to click on some of these to check them out. I think maybe I did them all. But you can read them in detail. Lots of different applications out there of a simple idea of just changing the basis that you're working in. Okay, I'll stop there. I'll be around for questions for a bit if you want to come chat, especially if you want to chat about your project. I'll be here. Okay, see you guys on Thursday.